Okay, I think we can get started. So I'm going to continue with information theory today, and I'm going to start with getting into essentially what a channel model looks like. So there'll be a lot of terminology. Hopefully I can get through that, explain what's going on, and then we'll focus on modeling a source. Start with channel source. Once you understand the source and the channel, then you can begin to understand the effect of the channel on the source, which is what the recipient is seeing. But what the recipient sees, the receiver sees, is what the source did, operated upon by what the channel did, and then what the receiver has to do is to figure out what the source meant to say. Okay, so you can think of something like a person who's trying to speak to somebody else in a different language. So the person who's speaking is speaking in some language, and the channel is a translator, and the recipient is trying to figure out what did the source mean to say, if the translator, made a mistake or not. If the translator is completely perfect, then we call that a noiseless channel. In other words, what the receiver got is exactly what the source sent. On the other hand, the translator may be imperfect, in which case you get a noisy channel. And of course, all channels in practice are noisy. So much of the work we're going to do in this is to study how to take into account the fact that a channel is noisy. Okay, so let's start with the model of the channel. So I'm going to first draw. Actually, probably need to draw it at the bottom. So this is the figure 4 in the text. I'm just going to draw all of it, but I'm going to do it piece by piece. So we have this notion of a channel, and the channel is something that repeatedly transfers. This is no good. Let's see, that's a midpoint, and I can draw that. Okay, that's much better. A channel is something that repeatedly transfers symbols from one end to the other. Okay, you can think of it as pick up its symbol, take it to the other side, and drop it off, and just keep doing that over and over again. From our perspective, that's what a channel is. Okay, I started out by saying a billboard, that you walk past on the side of a street, an advertising billboard is a channel. And in that sense, what it's doing is you can think of the advertiser as placing some symbols on the billboard. It's delivering it to you, and then a few months later they change the message, delivering that to you, etc. Or you can view the billboard as delivering the symbols from the board, from the advertiser to each passerby, as you wish, depending on what you're trying to model over here. But at any rate, you can Daniel, you can move in over there if you want. So that's a channel. So we don't actually think more about the channel other than it's repeatedly transferring symbols. Why it's transferring symbols, how it's doing it, etc. are hidden below the model. We don't really care about it. And this is something, by the way, that you should learn to do when you're building models for your own work. Okay, we will be doing research. What you need to do is to figure out what parts are essential and what parts are inessential in modeling a system. Every model is going to be necessarily wrong. Okay, as somebody said, all models are wrong, some models are useful. Okay, so if somebody says your model is wrong, you're going to say, sure, yeah, of course it's wrong, all models are wrong, but is it useful? Well, that's what you want to do. In information theory, this is sort of the lowest level of what's going on. This symbols being transferred from one side to the other. How that happens, whether it's a forklift carrying boxes full of symbols and putting it one side to the other, whether it's radio or TV or billboards or somebody speaking, we don't care. And that's what gives you the abstract power, because you can model all of them the same way. Now, what goes on into the channel are what I call channel symbols. Okay, and I want to distinguish between these symbols and the codes that we talked about last time. So the codes are coming from the message source. So the message source, I should be more careful, there's something called the source coder. So anyway, the message source is creating messages, and then we're going to code it. What we're doing in that coding is we're basically trying to remove all the excess redundant information from it. Okay, so we take this input and we say, okay, the intrinsic entropy here is only so many bits per message. I only want to code it that way, so all the extra stuff we take away. And what we saw with the Huffman code, for example, was that we tried to code over longer symbol sequences, right? And we tried to take into account the probability with which messages are coded, so that the expected coded message length on average is as small as possible. We can interpret that as saying we're squeezing out all the redundancy from the message. Okay, this is a very, very simple example. In many experiments that you'll do, you'll find that a typical value that you're logging is 0. Okay, you'll have lots of zeros. It's quite normal in computer science if you have lots of zeros. So a typical way of squeezing out zeros is you have 1,000 zeros, you just say 1,000 zeros, just write it out, 1,000 zeros, you don't need to say 0,000 times, right? So if you ever go to your D message on Linux, which is the console messages, you'll say so-and-so message below that, this message repeated, 200 times. Just say that. Okay, that's an example of removing redundancy. A very simple method of removing redundancy. If you use zip or compress or any of these utilities, that's all they're also doing. They're removing the redundancy. Okay, this is different. What we're doing over here is we're taking the channel symbols, we're choosing them in such a way so that the channel, when it comes out the other side, which are the error symbols, are so that there aren't too many errors. So if you choose this properly, there won't be too many errors, and I'm going to show that in a moment. And I now realize I'm drawing this the wrong direction, so let me change my tactics and show you so here's the message source that we talked about. And what the message source is doing, it's creating messages. So we saw this already, so nothing more to say about that. And what the message is doing, source is going, is they're going into source coder. And this is like a Huffman coder, for example. Okay. And what it's doing is it's taking all the messages as we saw before, uses a code book and spits out code words. Okay. And we'll call that message symbols. Now here's something I can do here which I can't do in PowerPoint, which is I can just move this down. There you go. So the message symbols we'll give to a channel coder. And what the channel coder is going to do, and we'll talk about this in great detail later on, is to take the message symbols, and I'll just say what we've done is we've removed redundancy. And a channel coder is going to actually add redundancy. I'll explain in a minute what it is, and that's going to go into the channel, and here we get the channel symbols. So this part should be clear, messages to message symbols, so removing redundancy, anything that's extra, throw it out because there's no need to send it, right? It's just extra stuff. So that's easy, we got that part last time. What's going on over here is that what we'll see is that the channel, when it's noisy, it's going to make things bad hopefully in a well-known way. Okay, and what does make things bad mean? It's going to convert 0 to 1 and 1 to 0. That's all we care about, right? All possible channel problems can be thought of as basically converting zeros to ones, ones to zeros, and we have two other things that might happen, insertions and deletions. It could add a 0 or a 1, or it might delete a 0 or a 1. But again, we won't model that. Over here, we're just going to assume that the channels always carry a bit, okay? And we can kind of fake it by saying that an addition of a 0 to 1, we'll view that as some kind of spurious process of adding zeros, and deletions, similarly can be modeled, but we're not going to do that. So the simple channel, noisy channel model is convert zeros to ones, ones to zeros. That's the thing. So if we know the way in which zeros can get converted to ones and ones to zeros, then we can do something clever over here. For example, just as an example, it might be that the channel converts zeros to ones very often and very rarely converts ones to zeros because of some physical characteristics. So zeros get converted to 1 a lot, but not the other way around. So what I would do over here is the channel coder would use mostly ones. Okay? If it uses mostly ones, it's going to get messages through. easily. Whereas if you use mostly zeros, it's going to get a lot of error. So by using mostly ones, okay, it will turn out that you'll need more redundancy, but the channel will be compensated for. Okay, that's what a channel coder is going to do. So we'll study that in a bit more detail. So on the other side, we have error channel symbols, as we saw earlier. And so once you get the error channel symbols, you're going to go into a channel decoder that's going to invert the process. What the channel decoder is doing is that it's getting these errored symbols and coming out with message symbols, and hopefully these message symbols were the ones that were actually sent. And then this goes into a source decoder, which then gives you the message. And that goes to the receiver. So I started out on Monday by showing you the source, the channel, and the receiver. That hasn't changed. What I've done is I've added into it essentially two extra pieces of mechanism, a source coder, which takes messages and removes redundancy. And of course, we need to decode it. That's on the other side. So we already covered that. And now we're kind of going one level below that. We're looking at the channel coder and channel decoder. And really from now until the end of this chapter, we're just going to focus on this section right here. This is all we're going to care about right now. Everything in this orange box, okay? So when I say symbol from now on, what I really mean is a channel symbol. When I say a source, I mean this over here. It's actually gone through the source coder already. So it's just, I'm calling it a source over here. And over here, I'm going to say receiver, I mean the source decoder, okay? Because I don't need to worry about that. From the perspective of the channel coder and the channel decoder, all that is above it somehow, right? It's a layered architecture, okay? Okay, any questions about this over here somewhere? Okay, so let me see. Let me make sure I've covered everything here. So there's a channel. Right, so let's look a little bit at the entropy involved over here. So if I have a message source, I'll model this as a random variable x, and the messages will be the domain of the random variable, which are x sub I. And I've kind of, I'm not telling you whether these are messages or sequences of symbols. For all practical purposes, we can treat these x sub I as being sequences of symbols, okay? The reason I don't really care is because I want to operate at this level over here. So we'll use x and xi, which we're using for the message source. We really want to kind of view that as being over here. And then x sub I here are going to be message symbols. It's like Huffman codes, right? We really want to just not talk too much about that. However, this is a code for the source, and that's a code for the source. So whatever the entropy is of this source, h of x, which is the intrinsic entropy of this source, this output over here cannot have a smaller entropy than that, a greater entropy than that. You can't add entropy, okay? So the entropy of this system over here is at least, I'm sorry, you can't reduce the entropy from what you have over here. So the entropy of this one is going to be at least greater than or equal to h of x. Okay, so if h of x is, in other words, let's say that we discover the message source has 20 bits worth of entropy. Okay, this one cannot reduce it to being less than 20 bits. It can make it more than, we can use more than 20 bits if you wish, but it can't use fewer than 20 bits. Okay, so this source code, or the output of this source code, no matter what it is, it has got an entropy of at least h of x. Okay, and similarly, output of the channel coder is going to have entropy of at least h of x. So h of x is sort of a lower bound on the entropy all the way down over here. Okay, because you have sort of this message source has intrinsically got a certain amount of entropy associated with it. We can't remove it. Okay, that's the minimum that we need. And so the result from the instantaneous code showed us that the instantaneous code will have entropy, which is this one over here, is going to have entropy of at least hx. Okay, and we'll see later that this limit holds true even if it's not an instantaneous code. Okay, I'll show that in just a moment. And so down here, we're going to have, again, the same thing. We're going to have a minimum entropy, which is here. It's going to have an entropy of at least that much. Okay, we can't take it out. It's what intrinsically is there. Okay? All right, so, okay. Now, the channel coder, as I said, is choosing these channel symbols. The big result, okay, the big result from Shannon is that if the channel symbols are well chosen, there exists a channel code such that the error, the effect of the error can be made vanishingly small. Okay, so even though the channel is causing errors, by choosing this channel symbol in the right way, the effect is going to be made as small as we wish. We choose an epsilon, I'll tell you how to do it. Sorry, there exists a code which has an error rate less than epsilon. Now, Shannon does not tell us what it is. Shannon just says such a code exists, and we'll see how the existence proof is done, and I'll sketch it out. And but Shannon did not say how. Later on, two other people found out codes which approach the Shannon limit. So in fact, these are in use today. Okay, if you use a cell phone, the voice coding that's going on for your voice and the data coding is actually using codes that are very close to the Shannon limit, and that really comes straight out of information theory. So everybody with a cell phone is using results straight out of information theory every day. Okay, so this has got some real practical consequences to it. Okay, so that's the main result that comes out of this. Okay, all right. So let me now move on a little bit and talk a little bit more about the channel, because we're doing this channel model. So the first thing about the channel is that we can talk about the channel as the simplest channel is called the binary channel. And a binary channel basically carries just zeros and ones. Okay, if you think about it, this is the simplest thing you could possibly do. So either it takes a 0 and takes it there, or 1 or takes it there, and that's all it does. Okay, and it's sort of the basic channel. And we can view these 0 and 1 as being two frequencies. They can be two amplitudes. They can be two phases. And we studied, when you're doing transform domain, how we can use phase shift or frequency shifting or amplitude to do keying, right? We talked about binary keying, right? So those are all the ways you can do it over here. But you can do better. So if you remember the queuing, we had this thing called quadrature amplitude modulation, and I talked about how we have these four phasors. So we have these four phasors, and where this is the real, this is the imaginary, and we choose the initial phasor values to be 0, rotated 90 degrees, -1, and then rotated 90 degrees over here. And so we get these. So when we have this, we are sending the message using a combination of both phase shift and amplitude. So the amplitudes are 0 over here and 1 over here, and we also have phase shift, okay, of π/2 and 3π/2. And so a symbol that's received, a channel that's described by this constellation diagram, as we call it, is going to transfer 2 bits, okay, with each symbol, right? Because it's sending this over here, so we get, this is what's called a quadrature, okay, QPSK, quadrature phase shift keying channel. And this transfers 2 bits per symbol. Okay? And we said, well, you can do better. We can actually do something like this. We can have, 4 like this, and then we can do another 4 like that. That gives us 8. And then we can do something, I don't know where, you could say 8 more, so you can do like this. Whatever. So you pick some bunch of stars which are separated both in amplitude and in phase, and this is what's called QAM 16, quadrature amplitude modulation 16. Oops. And this gives you 4 bits per symbol. Okay? So in practice, this is the probably the most sophisticated code in use today. And one question that I asked at that time, I kind of said, well, what happens if you use QAM 65,000, right? So you have 65,000 different positions of amplitude, quadrature, amplitude and phase. So you can transfer 16 bits with each symbol. Why don't we do that? And I said, well, it's because this channel is noisy. And now we'll see exactly what that means. Because when 16 bits are being transferred, these points are going to be relatively close to each other. So if you make a mistake in the amplitude detection, it's 65,000 points, right? If you make a slight mistake, you're going to get an error in the output. So 0 becomes a 1 or 1 becomes a 0. So the error rises. So there's sort of a practical limit to how much we can code depending on the noise characteristics of the channel. Okay. So we don't really need to know how this is done. From the perspective of information theory, all this is sort of a black box. We don't really care. All we care is, okay, how many bits are you going to give me per symbol? So it's important to realize that from the perspective of information theory, what we often call bit rate, okay, and what we call the symbol rate are different things, right? So symbol rate is intrinsically the rate at which stuff is being transferred over the channel. Okay, so symbol rate, if I say I'm giving you 1,000 symbols per second, that's the symbol rate. Okay. On the other hand, each symbol represents one bit or 2 bits or 4 bits. Okay, and then that's the bit rate. So you multiply that by 1, 2, or 4, depending on if it's a binary channel, a quadrature channel, or a QAM16 channel. Okay, and so we talk about the difference between symbol rate and bit rate. It's a pretty straightforward conversion. Okay, so the channel is defined by its what we call the right. So if let's say channel transfers C symbols per second, so that will be called its symbol rate, right? It transfers C symbols per second, and if the number of if C is going to be equal to 2 to the k, that means that we have 2 to the k possible channels, then the bit rate is going to be I guess I shouldn't really use that. That's not a good thing. If you have 2 to the k possible symbols, then the kc is what? It's just, so let's say you have 4 possible symbols, then we know that we're getting 2 bits of information for each symbol. So we say that there are kc is going to be the information rate which is going to be in bits per second. So this is bits per second, and that one is symbols per second. Okay, so that's the difference between the two, and it's called the information rate or the information capacity. So in some sense, we can think of the channel as being some kind of container which moves from one side to the other, kc bits per second. Okay, and it's got nothing to do with entropy. It's just the information capacity. Okay, so you can think of it as sort of the diameter of this information pipe. It can transfer so many bits from one side to the other. Okay, and we have to be careful to remember that when we did this over here, hx, the entropy was measured in bits. Okay, so the entropy was defined to be in bits. Here we're using bits in a slightly different sense. We're using bits in the sense of capacity. It's not that the channel is entropy. The channel is capacity. It turns out that the capacity has a very intuitive meaning in terms of bits. Okay, because it tells you how many bits of information being carried across, but it's got nothing to do with entropy yet. We're not talking about the channel having some intrinsic entropy. The channel is a capacity to move entropy across, if you will, okay, from one side to the other. So the entropy corresponds to message source, and this bits per second corresponds to the capacity, the information capacity of the channel. Okay, so is that clear? I mean, there's a distinction over here, because here the way we got 2 to the k possible symbols, we didn't have to do any sigma p log p kind of thing anymore. We just said, yeah, the channel can move 4 symbols, 2 bits per second, end of story. There's no probabilities involved over here. It's very straightforward. Whereas here, to compute the entropy, I need to know the probability mass function of the random variable x. Okay, so don't get confused between these two things. Okay. All right. The next kind of thing I want to, last definition is what's called a discrete memoryless channel. And a discrete memories channel is something what you'd expect. So discrete means that each symbol is separate. You know, when you send a message, when you send a symbol, the other side gets a symbol. It's not like the symbols run into the other. It's a discrete, sort of a discrete entity. It's not a continuous thing. Memoryless means that the channel has no memory. So if I send a 0 followed by 1, the probability of receiving the 1 is not affected by what was sent earlier. Okay, so if you remember, we talked about this notion of neurons, right? If your neurons, nerves in your body, if you send a message, an excitation message, it uses these ions, and the ions get into the system. And so the next time you send a message, it has a lesser probability of getting through till you get to saturation when you don't feel it anymore. Okay, so when you get a cut, there's some pain, but then the pain increases after a point. At this point, basically, you run out of ions, and you don't have any more messages anymore. That's a channel with memory. The fact that you're sending the messages over the channel causes the channel to change its internal state, and therefore, subsequent messages are affected. In this case, we don't have memory. We send something, there's nothing residual left in the system. So it's like a RF radio frequency channel. If I send you, a BPSK symbol over the air, over the radio frequency, the next time I send a symbol, the effect of the pass is completely vanished. There's no interference from one symbol to the other. Obviously, having memory makes it much harder, because then I have to do the output. The error rate depends not just on what I sent, but what I sent previously. Okay, and so we don't consider that again. Consider just a simple thing over here. Okay, any questions about this so far? This is sort of all I want to talk about in terms of the channels. So we're going to restrict our attention to discrete memoryless channels who have information that has an information capacity of kc bits per second, where c is the symbol rate, and we have 2 to the k possible symbols, and that's really all you need to know about the channel so far. For a noiseless channel. When you come to noisy channels, we need to know more about it, but we'll come to that later. Okay. Okay, so now let's go back to the message source. And for the message source, I'm going to be vague about whether that's the message source or that's the message source. From the perspective of the channel, it doesn't really matter. Okay, we can view this either as the output of a source coder, or we can assume that the message source has got no redundancy, so we don't have a coder. It doesn't really matter, okay? So I'm just going to model this whole box over here as one single thing, basically, when I talk about the message source over here. Okay? And which means that this together has some x is random variable and has some messages which are x sub I, or symbols that are x sub I, and we don't really care about that. Okay, so we essentially model this message source as having some intrinsic entropy h of x, which I already talked about. So the h of x is the intrinsic entropy of the message source, and we view the message source as creating messages that are put onto the channel. Okay, so the first kind of elementary thing we want to talk about is, okay, so how many bits per second of entropy is the source creating? So we view each message as having an entropy hx, and we remember that if you have two variables x and y have a joint distribution and the independent, then the joint distribution is the sum of the entropies. So remember that fact we had earlier. So if x and y are independent, then h of xy, h of xy is going to be h of x. That h wants to become a bracket for some reason. Okay, h of y, there you go. So therefore, if for the sake of modeling, I assume that the messages are independent, right? Then I get a very simple way to tell you what is the entropy of a sequence of messages, right? So I have this message x, and I tell you, okay, I have 10 messages per second being generated, for example. Then the joint distribution of the 10 messages, if they're independent, is just going to be the sum, okay, of the entropies. So the joint distributions h of, let's say, message 1, sorry, it'll be small x, x1, x2, all the way to x10 is just going to be sigma hx. Okay. Or actually, it's just going to be similar. I can just say 10, because it's 10 over here. I can just say 10 hx. Okay. So by assuming independence of the messages, we are able to easily tell what is the rate at which the message source is creating entropy. Okay. What do you mean by creating entropy? Well, entropy in some sense is the amount of randomness. Okay. So each message that is being generated by the source is a message that the recipient doesn't know about. Okay. Each message that is being created. So if I'm generating messages at the rate of 10 messages per second, that's 10 things that the recipient didn't know about. If these messages are independent, then the total amount of uncertainty created in the mind of the receiver as to what the messages were is just going to be 10 times the entropy of an individual message. Okay. If they're not independent, it's much more difficult, because in the joint distribution, who knows what it is, right? It could be a very, very large number of messages. But if it's independent, then we know each one can be treated independently. Then I can just simply do this. And so for the purpose of simplicity, I'm going to assume from now on that all messages are going to be independent of each other. Okay? And so that tells me this value over here. Okay? So if the message rate, so the message rate from the source is going to be m messages per second, and then the entropy of the source, entropy of a message, I should say, this is the same thing, is going to be h of x, then the entropy rate is going to be mhx. Okay, that's basically it. It's very simple. So let's take a look at the homework example so that this becomes a bit clearer. So in that case, I told you that the source had the source. So here, the xi, you can view them either as coming from here or from here. It doesn't matter. So but the table was basically xi, and then p of xi. And this was A and 0.2, B, 0.3, C, D, 0.25, 0.25. So just simple computation tells us that the h of x is going to be 1.98. Okay, that's the entropy of this particular source. Okay, if you round it up. And so I said that we had 10 independent symbols per message. So you have 10 independent, again remember it's independent, symbols per message. So the message entropy is going to be 19.8 bits. And that's going to be h of x. Okay, and then m was 10 messages per second. So the entropy rate becomes is just going to be 198 bits per second. Okay? So that was the answer to the first question, is 198 bits per second.
Is it okay if we approximate h of x
to 2? The reason why 2 is not a good idea is because if it were 0.25, 0.25, 0.25, 0.25, that would be equiprobable. And then that would be 2, right? What I wanted to show you was that this is a fairly significant change, of moving 0.2 to 0.3, yet the entropy only went down by only 0.02, okay? And so that's why I wanted you to do this as opposed to approximating it to 2. If you want to approximate it to 2, I'd say they're all equiprobable. Okay, so I really wanted to show you that it's, so you're supposed to be thinking about the homework, instead of just doing it. So okay, so if you say approximately 2, I suppose so, but I want you to see that there's something going on over here. Okay, any other questions? Okay, so the second thing, which is actually kind of an interesting part of this, is that if the entropy rate is mhx, then we can actually bound the number of distinct messages that are being created from the source. Again, distinct sets of independent messages that are being created. And so the upper bound, okay, which means that you can't have any more than this, is going to be 2 to the power mhx, okay,